So abhi tak we are dealing with functions of two variables. And when we see that I have a function of two variables, which is fxy equals to some constant, then we could find out derivative of y with respect to x using implicit differentiation. And now let us continue further to explore what else we can achieve from functions of the type fxy equals to c. So we will be dealing with general equations for the tangents to fxy equals to c. So we know that if I have a function of two variables, fxy, okay, and it is equal to a constant c, okay, and we know that y is a function of x, then we could find out that y dash, which is a dy by dx, it is minus fx divided by fy, okay. So the derivative was minus fx by fy, where fx is the partial derivative with respect to x and fy is the partial derivative with respect to y. That is first and second variables respectively. So if you have a lot of variables, we write it as minus f1 prime divided by f2 prime. Okay, we also know that y dash is nothing but the slope of the tangent to y is equal to fx at a designated point, whatever point we're talking about. So if you're talking about y dash at a point x naught y naught, so that will be minus fx at x naught y naught divided by fy at x naught y naught. Okay, so suppose what is happening, this is the slope of the tangent. Now your tangent is at the point x naught y naught, okay, and its slope is minus fx at x naught y naught divided by fy at x naught y naught. So if you look at equation of the tangent, how will you write it? So if you remember the point slope form of a line, so if a line passes through x naught y naught with a slope m, its equation will be y minus y naught is equal to the slope, that is this, okay, and x minus x naught. So if we simplify this, we will have fx x naught y naught multiplied by x minus x naught plus fy x naught y naught multiplied by y minus y naught. This is equal to 0. So this is the general equation of the tangent if a curve is of the form fxy is equal to c. You can look at the diagram. This is y is equal to fx, and this is the point x naught y naught. I'm drawing a tangent at this particular point, and this is the slope of the tangent at this particular point. Okay. Now you can see that the slope of the tangent. What is the slope of the tangent? The slope of the tangent is minus fx x naught y naught upon fy x naught y naught, the slope of the tangent at x naught y naught, which is, you can say, minus f1 prime x naught y naught if you go by this notation, divided by f2 prime x naught y naught, where f1 is the derivative with respect to x and f2 prime is the derivative with respect to y. Okay, so this is the slope of this particular tangent. Let this tangent be AB. Okay, now we know that if we draw a line perpendicular to the tangent at the point of contact, this line is called the normal. Okay, so what is the slope of normal at x naught y naught? So you know that the product of slopes of two perpendicular lines is always equal to minus 1. So slope of normal will be minus 1 times slope of tangent at that particular point, x naught y naught. So that will be f2 dash x naught y naught divided by f1 dash x naught y naught. This is going to be the slope of the normal at that particular point. Okay. So now let us try to see the geometrical interpretation and let us see some examples. Find the tangent to the curve in example 16.10. Okay, so what was the curve in example 16.10? So at 2, 1 by using, okay, 16.10, example 16.10. So we have to go to example 16.10. Okay, x cube plus x square y. So we want to find the equation of the tangent. So you know that this is x cube. Okay, so we have x cube plus x square y minus 2y square minus 10y equals to 0. So this is my fxy is equal to c. Okay, and now let us see what we have to calculate. We have to calculate the tangent to the curve. Okay, so what is the equation of the tangent to the curve? So we want to find out the tangent to the curve at 2, 1. So what was the equation of the tangent to the curve? Fx at x naught, y naught, x minus x naught plus fy at x naught, y naught, y minus y naught equals to 0. So x naught is 2, y naught is 1. Fx, the first derivative, will be 3x square plus 6 2xy. Okay, so fx at 2, 1 will be 3 into 4 plus 2 into 2 into 1. So which is 12 plus 4 equals to 16. And fy, so let's first calculate fy. So fy should be x square minus 4y minus 10. So fy at 2, 1 will be 4 minus 4 minus 10, which is minus 10. So my answer should be 16 x minus 2 plus minus 10 y minus 1 equals to 0. So now you can simplify this particular equation to calculate. Not a big problem. Okay, so we can always find the equation of a tangent at a particular point for a function of the type fxy equals to c. That's not very difficult. Now let us proceed. Okay. So the vector. So now just notice that we have f1 prime x naught y naught multiplied by x minus x naught plus f2 prime x naught y naught y minus y naught is equal to 0. So if you look at mathematics, if you look at the dot product of two vectors, the dot product of two vectors is defined as AC plus BD. So this is nothing but the dot product of f1 dash x naught y naught, f2 dash x naught y naught, and the dot product was with x minus x naught y minus y naught. The dot product is 0. Now, when the dot product of two vectors is 0, so if the dot product of two vectors is equal to 0, it means that those two vectors are orthogonal. This means that the vector f1 dash x naught y naught, f2 dash x naught y naught is perpendicular to the vector x minus x naught y minus y naught. Okay, that is what is meant by this. Now, this particular vector, okay, okay, it is denoted by del capital F x naught y naught. So it is the tuple formed by the first derivatives of the vector with respect to x and y. This is called gradient of fxy, okay, at x naught y naught. This is very, very important, and we know that the gradient vector is perpendicular to x minus x naught y minus y. Okay, now let us again consider one thing. If you remember that what was your directional derivative, okay, so if you remember that your directional derivative at a point h comma k was f1 dash xy dot h plus f2 dash xy dot k, where the norm of hk was 1. That means hk was a unit vector. This was the directional derivative. So if you look at this particular combination, okay, this particular combination, okay, this is also a directional derivative. Okay, if this particular vector has a magnitude of 1. So if x naught minus or x minus x naught comma y minus y naught, if the magnitude of this particular vector, okay, is equal to 1, then this particular expression is nothing but the directional vector in the direction of x minus x naught comma y minus y naught. Okay, so we can also relate the equation of the tangent as a directional derivative. Okay, now you can see that this, if you look at let's read this. If hk is a unit vector and del f x naught y naught is not equal to 0, then the scalar product is the directional derivative of fxy in the direction hk. That is what I'm telling you. So a movement of 1 unit away from x naught y naught in the direction of hk changes the value of f x naught y naught by approximately d. So if you look at the directional derivative is the dot product of f1 dash f2 dash with a unit vector hk. If you look at the definition of dot product, what is the definition of dot product of two vectors? Magnitude of a, magnitude of b, cos theta, where theta is the angle between vector a and b. So now, if you look at the dot product of these two vectors, the directional derivative is magnitude of f1 dash f2 dash, okay, magnitude of hk, and cos theta, where theta is the angle between this vector and this vector. So what is my vector here? My first vector is f1 dash f2 dash, which is the gradient vector. Okay, my second vector is the unit vector hk. Okay, and this is my angle. So if you look at my directional derivative, this is the magnitude of the directional derivative. Okay, this is the magnitude of the gradient vector into the magnitude of this vector is 1 cos theta. So directional derivative will be this. Okay, so now here the angle is phi. Phi is the angle between the vectors this and hk. Hence d attains its maximum value when phi is equal to 0. Of course, we know that the value of cos theta is less than 1 and greater than -1. So maximum value is at 1. So when phi is equal to 0 or when theta equals to 0. So when they both are aligning in the same direction, the directional derivative will be maximum. Okay, so when phi is equal to 0, the gradient vector points in the same direction as h comma k. Okay, so consequently, the gradient vector points in the direction of the maximal increase of fxy. So now we have the following results. So if the gradient vector is not equal to 0, then del f is orthogonal to the level curve that we have seen, because we could reach the conclusion that f1 prime, f2 prime at when multiplied with as a dot product with x minus x naught, y minus y naught, that was equal to 0. Del f xy points in the direction of maximal increase of fxy, because when theta came out to be 0, we noticed that the directional vector and hk had the same direction, because this was my hk and this was my del f, and when this angle became 0, then they came in the same direction. So this angle was 0 degrees. Okay, so now we have the formula for the second derivative. Okay, so we have already seen that if we have a function of the type fxy equals to c, my y dash is minus gx upon hx. Okay, so where this is minus f1 dash xy and this is f2 dash xy till this point we have derived. Okay, and where gx is a function, where gx is called the first derivative with respect to x and hx is called the first derivative with respect to y. Okay, now we are interested in calculating the second derivative. So y dash is minus gx upon hx. So y dash dash will be by quotient rule hx square hx g dash x minus gx h dash x. So now what is your gx? Gx was f1 x y dash. So when you do g dash x, so you are again with differentiating with respect to x now. So that is f11 dash xy into d by dx of this x, which is 1. And now f12 dash. Now I'm differentiating with respect to y, partially this thing, xy, and now dy by dx, chain rule. Similarly, if I talk about h dash x, so what is my hx? f2 dash xy. So now I differentiate with respect to the first variable. So it will be, and then I differentiate with the second variable. It will be, so we have double prime for second derivative. Okay, so these are the expressions which I'm supposed to, and always remember by Young's theorem that these two things are assumed to be equal. I'm assuming that the partial derivatives are continuous in nature. Okay, so by inputting all these things by g dash x and h dash x in this particular formula, I will be getting y dash dash equals to, so what is your, so there was a negative sign outside, so take a negative sign outside, and hx was f2 dash square, so hx was f2 dash and then f11 double dash plus f12 double dash into y dash. Okay, and then minus f1 dash. Okay, so gx was f1 dash and h dash is f12 double dash, because I'm assuming that this and this are equal. Okay, Young's theorem, and then plus f22 double dash y dash. Okay, so this is my expression. Okay, and replace y dash in both the preceding equations by the equations in 16, by the quotient in 16.9. So what is your y dash? So your y dash is nothing but minus f1 dash divided by f2 dash. So if you do this, okay, you will be able to get a formula, final formula. This I leave up to each one of you. This is a simple manipulation of calculating the second derivative of an implicit function. All right, and now you know this particular function can be converted into this, to remember, and this is a determinant. If you calculate this determinant, you are going to get this answer. So this also can be done as an exercise. And now if you look at this, so find y double dash when this is equal to this. So we just have to apply the formula. And what was the formula? This is the formula, 16.1. So we can calculate the second order derivatives also. So this is about general equation for the tangent plane. So how we could see that the gradient is orthogonal to x minus x naught and comma y minus y naught. That is, it is orthogonal to the level curve fxy equals to c. We could also find out the slope of the tangent at a particular point, the slope of the normal at the point of tangency. We could find out, and we could also find out the formula for the second derivative of an implicit function. And now you can apply these formulas in your questions. And even if you can't apply the formula, just go by the method that has been done. It's not a difficult task to carry out the calculations. Thank you.